Hey guys, so we got a fun one here. I've been wanting to do this video for a long time. So we are going to see where the trig graphs come from. And we're actually going to learn that trigonometry is maybe more closely related to circles than it is to triangles. Now if that sounds mental, bear with me. Let's go on this adventure. Okay, so first of all, we're going to need our three trig identities. So, sine theta is in a triangle the opposite divided by the hypotenuse. Cos of theta is the adjacent divided by the hypotenuse, and tan of theta is the opposite divided by the adjacent. So, first up, we're going to look at sine of theta. Okay, so then very roughly, here is our graph of y equals sine theta. So let's label some important points. So we go through the point 0, 0, and it goes through the x-axis at 180, and then again at 360. The peaks of the wave are a 1, and the troughs of the wave are a -1. Now the x-coordinate of this peak is 90 degrees, and the x-coordinate of this trough is 270 degrees. So those values are mirrored in the y-axis. So this is -180, this is -360, this peak is -270, and this trough is -90. So we are about to see where this comes from using the unit circle. Okay then, so here's our unit circle. Now a unit circle is a circle with a radius of 1. So this unit circle is centered at the origin 0, 0. So this point is 1, this point is 1, this point is -1, and this point down here is -1. Now a bonus question for you guys down in the comment section: what is the equation of this circle? Okay, so what we're going to do now, we're going to draw a radius in. So we're going to draw a radius, so that's going to come from the origin up to the circumference of the circle, like that. It doesn't need to be so thick. Okay, that'll do. Okay, so why have we done that? Well, what we can now do using this radius is we can actually turn this into a right angle triangle. Now, we call this angle here, it's always measured between the horizontal and our radius, anti-clockwise. So we're going to call this angle theta. Now, this is a unit circle, so we know that the radius is 1. So the hypotenuse of this right angle triangle is 1. So we are interested in sine of theta. So remember, the identity for sine is sine theta is the opposite divided by the hypotenuse. So here we get sine of theta is equal to the opposite divided by 1. Therefore, the opposite side is sine of theta. So that's very, very important, and this is going to help us explain where our graph of sine of theta comes from. Sine of theta is the height of any point on the circumference of this circle. So at the moment, our point would be that. If our point moves, then so does the radius of the triangle. So, or the hypotenuse of the triangle, sorry. So let's say our point was here. Then our radius would come out like that. And then our height would go down like that. And then this would go across. So now we would have a much smaller value of theta, and this height would now be sine of theta. So again, sine of theta is describing the y-coordinate of any point on the circumference of the unit circle. So I'm going to clear this up now and show you some important values. Okay then, let's start with when theta is 0. So when theta is 0, that would give us this point here on the circumference of the circle. So there would be no angle between the radius of the circle and the x-axis. The x-axis is the radius of the circle. So this would give us then theta is 0. So when theta equals 0, the height of our triangle is non-existent. There is no triangle. It's a straight line. So that tells us then, as we know from the graph, sine of theta is equal to 0. Again, because sine of theta is the height of this point above the x-axis. There is no height, so sine of theta is equal to 0. What about when theta is 90 degrees? So when theta is 90 degrees, we are up here on the y-axis. So that would give us our right angle there, and then we would have a triangle going across like that. So this time, when theta is 90, or sine of theta, the height of our point on the circumference of the circle is 1. So what's going on here, as theta increases, so as theta increases along this way, we approach further and further, closer and closer, the peak of our graph. So we are going closer and closer up to our peak of 1, which happens when theta is 90. So if we go back to the graph, we are now at this point. And then, once we've got there now, as theta starts to decrease, as theta carries on increasing, so as we keep going on and down here, so we get to, well, that would give us theta being 180, our point now would be over here, again on the x-axis. So this tells us that when theta is 180, sine of theta is 0. So what we've got up to there now is this first part of our graph. So we've gone all the way up to the peak. Our point got as high as it can go on the circle, and then it rolled back down around to a height of 0. So now as theta increases even more, so we now start going down around to here. So that's going to give us an angle of 270 if we go all the way down to the minimum point on the y-axis. So we're now here. So this would tell us sine of 270 is equal to minus 1. So that has taken us on this part of the graph. So we've rolled down around the circumference of our circle, and then finally, as we roll back up around, so if we keep going and we make a whole rotation around our circle, and then we are back. We've done the whole thing, the whole rotation. So we've done 360. We're back where we started. So that tells us sine of 360 is 0. So that's taken us on the graph. We've gone all the way up to our peak of 1. Then we've rolled down around the side of the circle, all the way down to minus 1, and then we roll back up, right to where we started. Now you might wonder, where does the negative part of the graph come from then? Well, that comes from if we went around the circle in a clockwise direction. So instead of going anti-clockwise, we would be going clockwise, which would generate a negative part of the graph. So everything to the left of the y-axis. Now the reason these graphs go on forever is we just keep rolling around the circle. So we don't need to stop when we got the sine of 360. We can go around again, get sine of 720. That would just be 2 trips around the whole circle. So that is how the unit circle helps us describe the sine graph. Now, here's an awesome little GIF to illustrate what's going on. Okay, so as you saw, as the line went anti-clockwise around the circle, the curve was being generated from the location of the point on the circumference. So watch it again. Good times. Okay, now we're going to do cos. Okay then, here is a rough sketch of y equals cos of theta. So let's again go through and label the important points. So again, the peaks are a 1 and the troughs are a minus 1. Hopefully you understand why this is now. Remember, we are describing the location of a point on the circumference of a unit circle. So this point can only ever be a maximum of 1 away from the origin. So cos goes through the x-axis here at 90, here at 270. This trough happens at 180, and this guy is at 360, Now cos is symmetrical through the y-axis, so this is minus 90, this is minus 180, this is minus 270, and this guy is minus 360. So now we're going to have a look at using the circle to see why we get this graph. Okay, so we've got exactly the same setup as we have with sine. So it's the unit circle centered at the origin. So again we got 1, 1, minus 1 and minus 1. Now then, what we're going to do is exactly the same thing. We're going to draw a radius from the origin out to the circumference of a circle, of the circle. Then again, we can make ourselves a right angle triangle like this, times again this angle is theta, and because it's a unit circle, again our hypotenuse is 1. So remember that cos of theta is the adjacent over the hypotenuse. So here, again the hypotenuse is 1, so cos theta equals the adjacent over 1, so the adjacent is equal to cos of theta. So this time, when we're looking at cos, we are looking at the horizontal location of the point on the circumference of the circle. So this distance is now cos of theta. So if our point was to move, say, to here, we would then have this triangle going on. So notice here then, theta would be smaller, but cos of theta has now got bigger, so it's getting closer and closer towards 1. Also notice here, sine of theta has got smaller. So sine and cos sort of have an inversely proportional relationship. As one gets bigger, the other one gets smaller. So I'm going to clear this up and we'll go through our important points again. Okay then, so let's start with when theta is equal to 0. So when we've got no angle between our radius and the x-axis, that's going to put us at this point here. So if theta is 0, that would just give us that line there. So that gives us then, well, cos of 0, well, this length here, remember we're now looking at horizontal lengths, is 1. So cos of 0 is equal to 1. So that's why the graph starts off at 0, 1. If we then rotate it around a bit to 90 degrees, so if theta was equal to 90 degrees, that would put our point up here. So we would now have this triangle, and then this would be our 90-degree angle. So we can now see that cos of 90, remember we're looking for the x coordinate. So cos of 90 is actually 0, because there is no distance from the origin along to our point. Our point is directly above the origin. So sine of 90 was equal to 1 because our point is 1 above the origin, but cos of 90 is 0 because our point is directly above the origin. So far on our graph, we have seen that, well, we've started off up here at 0, 1, and we've rotated by 90 degrees, which has taken us down to this point. And of course, someone has to ring me. Go another 90 degrees around and see what happens. So, if we now go to 180 degrees, that is going to take us over here. So we've gone for half a rotation around our circle. So we can now see that our distance has now gone down to, or our x-coordinate has now gone down to -1. So cos of 180 is equal to -1. So what's happened so far? When we started with theta equals 0, we were at 1. As theta got closer to 90, cos of theta decreases, so our value has decreased until we got to 0. But then, as theta keeps on increasing again, we start to get further and further away from the origin, and we just get down to a value of -1. So again, our point is physically 1 away from the origin, but the x-coordinate is -1. So that takes our curve then down to -1 because the value of cos of theta is -1. Okay, now let's continue our adventure around the circle. So let's go down to 270. Now that is going to put us here. So at this point, we are again no distance away horizontally from the x-axis, from the origin. Horizontally, we are just directly below the origin. So this tells us cos of 270 is equal to 0. And then if we do our last little trip around the circle, so if we were to go the whole 360, that takes us back to this point. So cos 360 is again 1, because we are back now at being horizontally 1 to the right of the origin. So that takes us back up to where we started. So on the graph, that takes us back from this point, first of all to 270, and then another 90 degree rotation takes us back to 360. So I'm going to find a nice little GIF to showcase this again. Okay, here's a nice little GIF then. So take note of what's going on the circle and where we are location wise on the curve. Now the reason we have pi's on the x-axis is because this is using something called radians, which you're going to see next here. It's just another way of measuring angles other than degrees. So pi is 180 and 2 pi is 360. So a nice little illustration. Hopefully this makes it make sense. Now we're going to look at tan and see again why it's such a mentalist. Okay then, so here's a sketch of our tan graph. Now notoriously it's the one that everybody can't remember because look at it, it is ridiculous. So what's going on here, these black dotted lines are called asymptotes. Now we actually met those before when sketching reciprocal graphs. So an asymptote is a straight line that a curvy thing can get infinitely close to but never touch it. So why does this happen with tan? Well, one of our trig identities that we're going to see later on is that tan of theta is actually sine of theta over cos of theta. So we run into a bit of a problem here whenever cos of theta is equal to 0, because then we are trying to divide by 0, which you can't do. It's undefined, it's naughty, don't ever do it. So these asymptotes happen whenever cos of theta is equal to 0. So 90 degrees, then again at 270 degrees, and then at minus 90 degrees, and at minus 270 degrees, and every 180 degrees to the left of mine under there, minus 270, and every 180 degrees to the right of positive 270. As for the x-intercepts, well, we got 0, 180, 360, and then every 180 degrees to the right, and minus 180 and minus 360. So we're going to attempt to use the unit circle to show why this looks so mental. Okay, so we now know that sine of theta is giving us the height of a point on the circumference of a unit circle, and cos of theta is giving us the length or the x-coordinate of that point away from the origin. So we can now write our circle like this. So again, we got the radius of 1, we got our angle theta measured anti-clockwise up from the horizontal. Now we can call the sides of our triangles sine of theta and cos of theta for the opposite and the adjacent. So we know tan of theta is the opposite over the adjacent. So here tan of theta is equal to sine of theta over cos of theta. Now we could be a little bit sneaky and think of this as tan of theta is the y coordinate over the x coordinate. That's probably the simplest way to think of this as we go through. So let's think about this. So if say we picked a point here, so really close to the y-axis, then here at this point I'm not going to attempt to draw it, am I? Let's attempt to draw it, it'll be fun. Okay, so coming out from the origin, our triangle is going to look something like this. Now bear in mind I can't draw, so the diagonal is meant to be coming out from the origin. The important things here to realise are, at this point, the y coordinate is large, but the x coordinate is small. So remember from our graph of tan, as we get really close to 90, the graph shoots off up to infinity. So what's going on there is, if you do a large y value divided by a really small x value, you're going to get a massive, massive number. So as we get closer and closer to touching the y-axis, this value, y over x, is getting bigger and bigger and bigger and bigger and bigger. Now we're going to get a problem when we touch the y-axis, but we'll talk about that in a moment. If we chose another point, so let's go for a point down here, really close to the x-axis. So somewhere like that. Now here, we've got the completely opposite situation. So at this point, again, remember I can't draw, at this purple point, this time the y value is small and the x value is large. So as we get closer and closer to the x-axis where theta is 0 degrees, this fraction y over x is going to be really small. So y over x approaches 0 as we get closer and closer to the x-axis. Again, because the y value is going to get really small, but the x value is getting bigger and bigger and bigger. So that is going to result in a really small number. So that's why towards our value of 0 on the x-axis, the graph sort of speeds up towards 0. So now I'm going to clear this up and we'll just talk about the important points one more time. Okay then, so let's just get it written down that tan of theta is our y coordinate over our x coordinate. Just makes things simple and I don't have to keep saying sine and cos. So let's first of all think about tan of 0. So when theta is 0 degrees, hopefully by now we are happy that we are at that point there. So when theta is 0, we get tan of theta. Tan of theta is, well, the y coordinate is 0, the x coordinate is 1. 0 divided by 1 though is 0. So tan of 0 is 0. Let's go up to 90 degrees. Stylus is running out of life. Good times. So when theta is 90 degrees, we are up at this point. Now, we get a little bit of a problem up here. So tan of 90 is, well, our y coordinate is now 1, our x coordinate is 0. Now, we got a problem there then, we can't do that. You can't do 1 divided by 0. So that gives us an unhappy face, because we can't do that. It's undefined. So that is the reason that we get our asymptote at 90 degrees, because we can't define that as a value. So what happens again, as we're coming up closer and closer to this point on the y-axis, the graph is shooting off to positive infinity, because you've got a large y value divided by a smaller and smaller x value, but as we hit the y-axis, we're doing 1 divided by 0, which we can't do. So the graph can never, ever touch the y-axis. So then if we go around another 90 degrees, so we go all the way around to 180 degrees, well, that puts us here at this point. So tan of 180 is going to be, well, our y coordinate is 0, our x coordinate is -1. So it's just 0 divided by -1. Now that is just 0. So what that's given us is this point here. So how do we get this negative part of the graph? Well, remember, between here and here, y is positive, so y is greater than 0, but x is negative. So we are doing a positive value of y divided by a negative value of x. So therefore y over x is going to be less than 0, negative. So that's why we get this negative part of the graph, because we are doing a positive y divided by a negative x. Okay, what about the next important point then? So the next important point is 270. So again, we get the same problem. So down here now, tan of 270 is, well, our y coordinate is -1, but our x coordinate problematically is 0. So again, we're unhappy there. That's why we've got an asymptote at 270 degrees there. Now, why do we get this positive part of the graph? Well, on this part of the circle now, y is less than 0 and x is less than 0. They're both negative. Therefore, y divided by x, negative divided by negative, gives us a positive value. Okay, and then we got one last trip to make. This must be a really long video. If you're still here, hold on. So the last one we need to look up is 360 degrees. So, at 360 degrees, we are just back where we started. So again, we get that value 0 over 1, which is equal to 0. Now down here, this time we've still got y is less than 0, but x is greater than 0. Therefore, y divided by x is gonna be less than 0. So that is why on our final part of the graph we've got this negative part of the graph going up to 0 on the x-axis at 360 degrees. Right then guys, that's it. So that is where our trig graphs come from. They are so closely related. In fact, they are related. They are the points, the locations of a point on the circumference of the unit circle. I hope this has helped. I've enjoyed doing this. Take care.